Okay, so in this video for Math 1560 Calculus 1 at U of L for fall 2017, we're going to look at a couple of examples using the definition of the definite integral to actually evaluate some integrals. So we're gonna set up this definite integral as a limit of Riemann sums, and we're actually going to try to compute this thing. We're going to try and find this limit as n goes to infinity. Okay. So here's an integral that we've seen a couple of times. We played around with this, and we kind of, by looking at what we had done so far, we got the feeling that this integral was going to be somewhere around 8 over 3. And we want to see whether or not this is exactly the case. All right. So what we do is, the first thing we do is we set up our partition. Okay. So our partition is going to be this. Our delta x is 2 minus 0 over n, so 2 over n. Okay. Our xi is going to be x naught plus I times delta x, and so x naught is just 0, so this is simply 2I over n, and so we want xi squared. Well, that's 4I squared over n squared. Okay. So what we're going to do, we're going to set up a Riemann sum, and we're going to use right endpoints. And one of the things that we're not going to prove this, but one of the things that is true about the integral is that if the integral exists, once we take this limit, letting n go to infinity, it doesn't matter if we use right endpoints, left endpoints, midpoints. Excuse me. It doesn't matter how we choose that point. We're going to get the same value, right? And one way to think about this is, as n gets bigger and bigger and bigger, the width of those rectangles shrinks. They become skinnier and skinnier and skinnier. And so the difference between the left endpoint and the right endpoint becomes tiny as n gets larger and larger and larger. So if we use right endpoints, then our Riemann sum, which is the sum, I going from 1 to n, of f of xi delta x, looks like this. It's the sum, I going from 1 to n, of 4I squared over n squared times 2 over n, right? So our f of xi is xi squared, our delta x is 2 over n. So remember we had this formula last time. There's a summation formula that said that the sum I going from 1 to n of I squared, and again, you don't need to know this formula, but we do need to use it for this problem. There's this formula that says that's the sum of I squared, I going from 1 to n. So if you use that here, what you find is, so there are some constants that we can bring out of the sum. 2 times 4 is 8. N squared times n cubed, right? That 8 over n cubed is a common factor for I equals 1, I equals 2, I equals 3 for each copy of I all the way up to n. Okay, so 1 to n of I squared, and now we plug in this summation formula, and so what we get is 8 over n cubed times n plus 1 times 2n plus 1 over 6. Okay, and now we're going to do a little bit of simplifying. So one of the things we'll notice is that n plus 1 over n, 2n plus 1 over n, right? So what I'm going to do, the first thing I'm going to do is I'm going to cancel this n with one of those. So there's an n squared, right? And then that n squared on the bottom is n times n. I've got two n's sitting there, so I can put one of them with the n plus 1, the other one with the 2n plus 1. And if I divide everything by n, n over n is 1. So 1 plus 1 over n. The other one is 2 plus 1 over n. And 8 over 6, well, that's 4 over 3. So what I get here is I get this. I get 4 over 3. Once I simplify, I get 4 over 3 times 1 plus 1 over n times 2 plus 1 over n. Okay, so there's my Riemann sum with n rectangles, right? So if you put in, say, n equals 10, 20, whatever number of rectangles you want to use, that's going to give you your approximate value for the Riemann sum. And using right endpoints is going to give us a bit of an overestimate for the true area, and the overestimate comes because we're adding in this 1 over n and this 1 over n. Okay, the integral from 0 to 2 of x squared dx. So we defined this last time. It's the limit as n goes to infinity of r n, and so this is we'll say f, and Pn, partition with n rectangles. Well, that's what we just calculated. So this is the limit n going to infinity of 4 over 3 times 1 plus 1 over n, and then 2 plus 1 over n. And of course, as n goes to infinity, what happens to 1 over n? Well, 1 over n is going to go to 0. So this becomes 4 over 3 times 1 plus 0 times 2 plus 0, which comes out to 8/3, and that's our integral. Here's an exercise for you to try. Try to do this in a little bit more general way. Try to show that the integral from a to b, so don't say what a and b happen to be, but try to show that the integral in general from a to b of x squared times dx ends up being b cubed over 3 minus a cubed over 3. Everything looks more or less the same as what we just did, except your delta x is going to be b minus a over n, and your xi is going to look like a plus I times b minus a over n. So the algebra is a little bit more complicated, but the outcome is the same in the end. So you can give that a try if you're interested. Alright, well, here's one more example. Now this first one, a couple of ways I can do it, right? So let's say for the integral from 0 to 3 of x plus 1 dx. So here's sort of plan A. We say, alright, delta x is 3 over n, my xi is 3I over n, my f of xi is 3I over n plus 1, and so my Riemann sum looks like this, the sum I going from 1 to n of 3I over n plus 1 times 3 over n. And we can split this up. We'll talk properties of summation in the next video, but using some basic properties for summations, I can split this up. So if I push the 3 over n through here, I've got 9 over n squared times I plus 3 over n. That's what I've got inside. And I can do my summation one term at a time, and I can pull out the things that don't depend on I, the common factors. So I get 9 over n squared times the sum of I plus 3 over n times the sum of 1, I going from 1 to n. And what we find, again, there are some summation formulas. I going from 1 to n of I. This is n times n plus 1 over 2. Sum I going from 1 to n of 1. Well, it's just adding 1 to itself n times, so you get n. So what we get here is 9 over n squared times n plus 1 over 2, and then 3 over n times n. Okay, so that seems to suggest that my integral should be the limit as n goes to infinity of, and let's clean things up a little bit here. I can cancel those, I can cancel those, and so I get the limit as n goes to infinity of 9 over 2, this 2 here, and then I have n plus 1 over n, and then I have 3. Okay, and so what are we going to get? Well, the n plus 1 over n, again, that's 1 plus 1 over n. This is going to go to 1 in the limit. So I get 9 over 2 times 1 plus 3. So 9 over 2 plus 3, which is 15 over 2. Okay, now, if that's plan A, there must have been a plan B. Right? There's another way we could have done this. We could have been smart about it. We could look at a graph. What does this thing look like? 1, 2, 3. Well, it's just this. It's just... So this is 3, 4, 0, 1. Okay, so the area I'm calculating is the area of this trapezoid. Okay, and there's two ways I can do this. I could do it as kind of, well, hey, it's a rectangle plus a triangle. Area 1 is 1/2 times the base 3, right? We're going 3 units across, times the height, which is 3, 9 over 2. What's area 2? Area 2, well, that's just the rectangle. Base is 3, height is 1, so it's 3 times 1, which is 3. And notice those are exactly the values that we had, right? The 9 over 2 plus the 3, we get our 15 over 2. And I guess you could have also done this using perhaps a trapezoid rule. If you know the formula for the area of a trapezoid, you would get that 15 over 2 as well. Now, what about the other integral? You could try to set it up as a Riemann sum, but I can tell you right now that it's going to be hopeless. You're not going to get anywhere. Here's a case where it's better to be smart and think about what that integral is actually computing. So now we come back and we say, well, we had two ways to think about the integral, right? Either limit of Riemann sums, but also we can think in terms of this signed area. And what kind of area are we dealing with here? Well, what is our graph? Our graph is just the top half of the unit circle, right? So we know what the area is. The area is, it's half of the unit circle. So the area of a circle is pi r squared. So pi times 1 squared. Okay, and it's half of that. So what is the area? Pi over 2. And that area there must be my integral. Right? So this time we can evaluate the integral not using calculus, but simply by using a bit of geometry and using known geometric formulas to recognize, okay, this integral actually represents an area that I know how to calculate without using calculus, so why would I try to do it using calculus? And in fact, doing this area with calculus, that's not an integral you'll learn how to evaluate until Calculus 2, and even in Calculus 2 you're going to find that that's not a particularly easy integral to evaluate. So sometimes you are much better off, you know, drawing that picture. It never hurts to kind of pause for a moment and take a look at what exactly you're computing to see if you can perhaps come up with a shortcut.